Hi, everybody. Today we are pivoting into the more practical side of Bayesian statistics, where we're going to rely on numerics to calculate complicated probability density functions that we wouldn't be able to otherwise do analytically. And the idea behind here is to get into MCMC, which is Markov chain Monte Carlo methods. And this is a core technique for using Bayesian statistics in the context of data analysis. And we want to understand the principles behind this numerical approach before we get into doing practical applications. So without further ado, let's think about why we call this a Markov chain Monte Carlo, and why would we want this. In the previous lecture on regression, we wrote down a bunch of posterior distributions that were functions of data, and they were functions of the prior distribution. And the number of parameters and hyperparameters in that problem started to get uncomfortably large. For example, I worked a mixture model problem where I had to fix one of my parameters in the mixture model because otherwise I wouldn't have the computational fortitude to go through and sample the entire distribution, locate its maximum, carry out the integrations and maximizations that I needed. Now, I was doing things simply, and there are ways of getting around that for that particular problem, but the simple case of merely 7 parameters is something that we would not really worry about too much in the optimization space, but it's very easy to get up into tens or hundreds of parameters in a Bayesian data model. As a result, what we're going to need to do is to come up with a numerical method that is going to draw from that posterior distribution. And our goal is to design an efficient tool that allows us to grab samples from a known probability distribution that I'm going to call P of X. And then if I can draw a bunch of samples from that, I can both integrate over that distribution, and I can also calculate the statistical properties of it based on its samples and using things like expectation value, means, medians, etc. to determine the properties or the central parameters of that posterior. So note that in my notation here, I'm going to be just assuming that X is some big vector valued input to our function, and then we're going to get a scalar probability density function as an output. Now, this is not necessarily going to be a proper PDF in that it does not necessarily have to be properly normalized. And that's a problem because of these big high-dimensional functions. To normalize them, we would need to integrate over them. And if we integrated over them, we wouldn't have to do anything fancy here. But these are things we cannot intrinsically integrate over in a computationally tractable form. So what we're going to do is we're going to try to calculate the properties of P of X given X. So we are able, if I give you an X, we're going to be able to figure out what P of X is for that X. But we can't do it because X is for all possible X, or a representative set of X over, say, a giant grid, because X can be very high dimension, 10 hundreds of dimensions coming in. So that's the goal. We can calculate P of X. It is not necessarily properly normalized, and we want to be able to draw samples from it and then integrate over that distribution from the result. So to do that, let's consider not Markov chain, but Monte Carlo. And Monte Carlo integration is a technique that we use a lot in physics, where we are going to try to figure out what the integral of a complicated function is, use it without actually tabulating a value. You could do like rectangle or grid methods to tabulate the function, but one way of drawing a complex function or evaluating a complex function is to use a Monte Carlo approach. And so the idea is to just you take a set of x of I in a domain of volume or hypervolume V that is bounds P of X. Now, I'm kind of being I'm missing some details here because I say this is a compact function, which means it's either formally closed and bounded, or it goes off very rapidly as you get to infinity, so that you can write down a boundary outside of which the contribution of the function is negligible. So, given that, you throw a bunch of points into this domain, you evaluate p of x on that set of points, and then the integral of p of x is just the average value of those of those points evaluated with p times the volume. So it's fairly simple. This is like the average value. You're taking advantage of the average value of a function is essentially the integral divided by the volume over which you're integrating, and so you just multiply up that volume for something where you can actually calculate what the average value of a function is. Now, this requires careful sampling of the space. It requires, coming up with volumes that you can calculate. You can do a bunch of other tricks to facilitate this Monte Carlo integration, but its basic idea of that's going to follow through in Monte Carlo integration, which is if I find a bunch of values on a function, I can approximate its properties by just studying the properties of those samples. Another application of random sampling is to figure out how to draw random deviates from a probability density function. Let's say we don't actually have a nice specified generator for this PDF, but we can calculate the PDF given an x value. So an example for that is shown here, where this curve represents some wacky PDF that we nominally aren't able to sample from. And we want to nonetheless draw a bunch of deviates from this. Now, in 1D, this is kind of a fake example. It's fairly straightforward. You calculate the cumulative distribution function, you sample on the y-axis, and then you go ahead and transform it into the x-axis. So univariate sampling is always easy. But the problem really is high dimensions, illustrated here in one dimension. So what we do in a case like this, where we're trying to draw random deviates from a sample, is we just go ahead and pick a bounding function. Here, this blue function f of x is always larger than the scalar value p of x for everywhere in the relevant domain. And what we want to do is draw a bunch of points inside the rectangle of f of x. So this blue rectangle here. We just throw down a bunch of points, x and f of x, and those combine to sort of populate this space uniformly. And what we're going to do is we just take all of those points and we just reject anything that has f of x larger than p of x. And so we'll fill in all these random samples down here, and those will very naturally fill out the space and give us samples from the PDF, and then everything up here we just reject. Now, you may recognize, given this method, part of the problem as we move into higher dimensions, which is it can kind of get challenging and computationally inefficient to put points into the acceptance region of this sampling space, given some bounding function that we know. And let's consider an example of this. And let's think about what happens when we have a Gaussian, a normal distribution with standard deviation of 1, and we want to bound it by a sphere of radius 10 in n dimensions. Now, that radius 10 sphere will bound most of the probability density function, but there's still some infinitesimally large contribution from p of x outside what is equivalently 10 sigma in this space, but we'll say it's approximately going to contain all of the PDF. And in that case, we have a PDF for this Gaussian that is 1 over 2 pi to the n over 2, where n is the dimension, e to the magnitude of x over squared over 2. So x is the vector from the origin, in this case, in high dimension. And so that gives us this nice PDF. And we're cheating because we know what the integral of this PDF is in high dimension. You integrate it and you get 1 to the n, which is about 1 for this PDF. Similarly, f of x here is going to just be this sampling sphere. We're going to decide that the sphere has a function value of 1 out to a radius of 10 from the origin, and then 0 beyond that. So it sort of forms this, this hypersphere in the two-dimensional space. And we can calculate the area of that hypersphere in n-dimensional space, and get that the function here, where it's r to the n, pi to the n over 2, over the gamma function of n over 2 plus 1. So that's a nice tabulated result. I remember seeing it in statistical mechanics. Maybe you've seen it before as well. And we want to consider the ratio of the PDF volume in n dimensions to the radius of the bounding function in 10 dimensions, or n dimensions. And that's shown here. So this shows as the dimensionality n grows, how big is the PDF relative to the bounding volume here. And as you can see, it drops off. And the trick here is, of course, to notice that this is a logarithmic axis, so that by the time you are at n equals 20, you are at something like 10 to the minus 18. So the volume of the acceptance region is 1 part in 10 to the 18 of the volume of the sampling sphere. And bringing this down to like a radius 1 sphere or a radius 2 sphere doesn't actually solve this problem. It's still an infinitesimally small part of this sphere. And as a result, if you're just randomly sampling here, what you're going to do is only 1 in 10 to the 18 samples will actually hit inside your acceptance region. And 10 to the 18 numeric draws is a huge amount of data. So, this is, it is beyond exabytes worth of data just to try to sample once. So this brings us to Markov chain Monte Carlo, which is the solution to the dimensionality problem. And the unique insight of Markov chain Monte Carlo is to assume that the points we're going to construct a chain of samples. And this is distinct from before, where all the samples were independent. Now what we're going to do is we're going to assume that each of these samples in sequence is going to depend somehow on the previous one. Let's fill out that dependency as we go. So we establish this chain. It is a Markov chain in the sense of a physical process, and we'll get into the details of that soon. But we assume that we start at some x naught and we go through the chain x1, x2 to xi, all of which has a sort of neighboring relationship that depends only on the preceding point. So x sub I depends only on x sub I minus 1. And I like to think about this as the chain is stepping around in an n-dimensional space, and we define where it steps to in an n-dimensional space as a function of where it is and where it's going to, and we establish a transition probability to take a step. So this capital big P is the chance of going to xi given xi minus 1. Otherwise, if it fails to meet that probability, it stays at xi minus 1. So it's basically walking around and trying to take steps in this high dimensional space, and this capital big P is the probability that it makes that step. If we choose that big P such that we fulfill the condition of detailed balance, which is the probability density function that we're trying to get to, evaluated at xi minus 1, times the transition of getting to xi from xi minus 1, if we set that equal to the transition of the probability of being at xi minus 1, and then the transition to go to the position at xi minus 1 times xi, if the product of these two probabilities is equal, then you can go through the unique insight of Markov chain Monte Carlo, means that you end up having this chain sample P of x ergodically. And that means ergodically in the physics sense. So you think about a high dimensional space, and this is a trajectory in it. Normally, we think about this in the context of a phase space, a position momentum phase space. And we think about a system moving around in position momentum phase space and sampling all the possible states proportional to, say, a Boltzmann factor or something like that. So we see this a lot in statistical mechanics, but the ideas, while, and this is important to stress as a physicist, they came from physics, it has been generalized to a much broader sense, set of statistics. But the key insight is that this random walk process, subject to the constraints of detailed balance right here, end up sampling this space ergodically. So it wanders around in the space, but over time, it visits every part of the space with a probability proportional to P of x. So that's clearly something that is exactly what we want. If we end up with this chain, it will wander around, and then if we take the sort of ensemble history of a chain, it will represent statistical draws from P of x. So it's this great insight, and it's one of those things that as physicists, we have this great leg up on understanding it because we've been thinking about this in the context of statistical mechanics and the states of systems all the time, and we just kind of get to leverage all of that knowledge. It's great intuition. It is the intuition that motivated this discovery and computational innovation. So if you think this sounds like something you've already heard, you're absolutely right. Okay, so with all of that enthusiasm as preface, let's think about how to actually implement a Metropolis-Hastings algorithm. So Metropolis-Hastings is the sort of original Markov chain Monte Carlo model. Metropolis was a physicist and sort of wrote the first kind of physics paper on this, leveraging this idea of ergodicity to describe how to sample from these probability density functions. So what we want to do with our algorithm is to identify a transition probability, P of xi plus 1, given xi. And if we can find this transition probability and use the proof that was established with, associated with the kind of statistical mechanics of this under detailed balance, then we can sample P of x. So that's what we get. And the way we do this is we introduce what we call the proposal distribution. And that's another probability function, Q, that says, all right, Q of xi plus 1 given xi is a statement of how do I find xi plus 1 relative to xi. And the intuition here is that this is the probability density function of taking a step in this high dimensional space. And so like if it's say a Gaussian PDF or something like that for a proposal distribution, you are likely to take a step that's of order the standard deviation of the Gaussian, and you are unlikely to take a step that's 30 times the standard deviation. So that gives us kind of an intuition for what this proposal distribution is. So we can choose a multivariate normal, you can be uniform in some sort of n-dimensional sphere, doesn't matter. So you can set that as your distribution. The proposal distribution is ideally symmetric in its arguments. So the probability of going from x of I plus 1 to x of I, so taking a backward step, is equal to the probability of getting to xi plus 1 from xi. So it's kind of symmetric under argument interchange. So like a Gaussian, anything that depends on the distance between the 2 points and not the orientation will automatically fulfill this, because you can always interchange 2 points and get the same distance. Okay, so we're going to then draw from this proposal distribution to find out xi given get x1 given some starting x0. And this is basically a random walk process. You see why physicists get really excited about Markov chain Monte Carlo? Okay, so let's work this with a cartoon. So let's imagine that we have some initial point here, x0, and then what we have is this proposal distribution here shown in the yellow, that's q of x1, and we will generate a random step somewhere within here, and then take that step from x0 to wherever it ends up. And we say, oh, there it is. So we choose a random deviate, and it ends up stepping over here. So x0 to x1. Then we say, all right, we've made this step. We can then go to x1 and consider the proposal distribution for x2 around x1. So again, it's this Gaussian here, and so it's likely to be in this range, unlikely to put x2 way over here, and there's our sample x2. And then we can continue the process, centering our proposal distribution on x2 and draw x3, x3 to x4, and so on. So this proposal distribution random walks the point around, and the proposal is essentially setting the PDF for the step size. Okay. Going back to the Metropolis-Hastings algorithm, we're going to start at x0. We're going to figure out what an x1 is. And then what we do is we actually label x1 as a candidate. We don't necessarily take the step. Instead, what we need to do is we calculate the probability of taking that step. And so it's called the acceptance probability, which is alpha in my labeling here. So it's alpha of taking x1 given x0 is just going to be the minimum of the ratio of 1 or the ratio of probabilities, the probability of x1 over x0, times the ratio of the proposal distributions of x0 given x1 and x1 given x0. I'll just note here, I'll say it again in a moment, that if we have a symmetric proposal function, this term cancels out, and it's easiest to see that this is just the ratio of the probabilities. So if P of x1 is larger than P of x2, so this is the thing we're trying to sample from, this value would be larger than 1, and then the min function will just return 1. So the acceptance probability, if we are going up to a higher point on the PDF, is 1, and then what we do is we take a random number on the on 0, 1, and then we look and compare whether that R is less than the acceptance probability, and we will accept x1, take the step. If it's not, we're going to just set x1 equals x2, x0, don't take the step. And then you basically stick this all in a while loop and say, while you are less than some specified maximum number of steps, repeat the process. Go draw a new step from the proposal distribution, label as a candidate, calculate its acceptance probability, draw R from the uniform PDF, check to see whether to accept it, and then continue on. So you'll just start walking around with step sizes set by your proposal distribution, and your decision of whether to take a step set by the ratio of the probabilities that you can calculate. So remember, under our setup, we can always calculate the PDF, but we can't sample from it or integrate it. Okay. So setting this up, the genius of the Metropolis-Hastings argument is that this quantity, Q, proposal distribution of xi plus 1 given xi, times the transition probability of going from xi to xi plus 1 fulfills all of the criteria that we need for a probability, transition probability, that will then fulfill the conditions of detail balance, and we get a nice sampler from our PDF. So again, this is a note that if the proposal distribution is symmetric in its arguments, then that term in the acceptance cancels out and it just reduces to the ratio of probabilities. Essentially, if you are taking a step to a more likely space, you always accept the step. And if you're taking a step to a less likely space, you sometimes accept the step proportional to the ratio of the probabilities. All right, so that actually establishes what the algorithm is, but I think the best way is to actually look at one of these algorithms in action and decide sort of how to evaluate it in that context. So let's imagine sampling from a one-dimensional Poisson distribution. Again, this is a solved problem, and we could just use implemented algorithms to do it. But what I want to do is just sort of show how it would work in this case, in a case that's tractable, so that when we see the more difficult things, that makes it easier to understand. So a Poisson distribution just follows this functional form where the probability of getting n samples out of a distribution is some event rate lambda to the n power e to the minus lambda over n factorial, where n is non-negative integer. So this is technically, I guess, a probability mass function or something like that, since you can't have anything between the integers. So what we're going to do for our proposal distribution is to draw a random number r from the uniform distribution. If r is less than a half, what we're going to do is going to say xi plus 1 is going to step down as an integer, and then if r is greater than 0.5, we're going to step up as an integer. So it's a very simple function. Basically, flip a coin. If it's tails, you go negative. It's heads, you go positive. Take a step that's 1 unit wide. It's obviously symmetric because once I am at my new step, I have an equal probability of going back to my old step. So I could just simply replace the arguments here, and I would get the same PDF. We will always kind of end up with this case where we're just sort of having a nice, simple acceptance criterion that depends on the ratio of the probabilities. Okay, so given that, let's take a look at an example implementation. Now, I've written this up in Python, and I just kind of want to walk through how this works for sampling from the PDF and what it would look like in actual code space. So I would specify my probability, my event rate in my PDF. I call that lam because I write in Python and lambda is the anonymous function name. So let's not call it lambda, even though it's a really useful physics variable. It's just lam. I'm going to say I want to take 10,000 steps in my Metropolis-Hastings algorithm. And I'm working in a namespace where ss is scipy.stats and np is numpy. And what I need to do is start at some initial point, and then I initialize my sampling variable to be a vector of zeros with length of n steps. So I start out at 20. 20 is a bad choice of a place to start for where the event rate is 5, but useful to see what happens when I do that. Okay, then I need to come up first with my proposal distribution. To do that, I say, okay, I have some random deviate. I'm going to draw it from the uniform distribution. If it's less than a half, I take a step downward. And if it's more than a half, I implement +1. So I've labeled this my candidate. XC is my candidate point. And then I need to check the acceptance probability here. So what we're going to do is we'll take its np.min, so the minimum of the two values. It's either 1 or the ratio of the Poisson distribution at xc relative to where we are in the chain. And then if I have this, I say, okay, if my random deviate on 0, 1 is less than the acceptance fraction, I take the step. Otherwise, I stay where I am. that's all there is to a Metropolis-Hastings algorithm. What I've done here is note I can calculate the Poisson probability. This is just a function that's e to the negative lambda, etc. Lambda to the n, e to the negative lambda over n factorial. That's all this is calculating. And then all I got to do is set up a proposal distribution. You could do this easily as well. And then all we're going to do is run this. So let's take a look at what the results are. So this is my initial point. And what we're going to see is we're going to see what happens to this walker as it walks around. Remembering my event rate is 5.33333 or something like that. And then this is going to walk down and kind of sample the probability density function. This is counted as the number of steps, and there we go. Okay, so you can see it's walking around in this space, and as the number of steps increases, it just kind of moves along, bouncing around at about the event rate. So it just kind of ticks along here, and we're not going to watch this all the way to the end. This can go to all 10,000 steps, but the animation kind of looks like this through the entire process. Okay, let's change things up and take a look at the resulting probability density function. So what I'm doing here is I am keeping track of the full Markov chain that's here. And all I'm doing is I'm plotting a histogram of it in the x-axis. This is step 0, so we haven't started. And this little blue triangle is indicating where my sample is. And the red points here show the true answer, which is the PM probability density function actually calculated at these points. We're starting down here where it's essentially 0. And as we take samples, you'll see this density function. The walker is bouncing around here between x at different x values. And as we go through the steps, I am jumping up the size of the steps through this animation. You can see that we converge to the Poisson probability density function. Still a few fluctuations around it, not quite perfect. Would need more samples to get there, but it gives you a sense of the PDF. So we can watch that again. You know, I started at 20, and eventually the contributions out here get swamped by the rest of the points. So eventually the walker is mostly bouncing around in this range near the sampling rate, but occasionally it makes steps over here. Okay. The walker actually gives us a couple of illustrative points that are very useful for thinking about the more complicated case. First off, I started far away from the peak of the PDF, and it took some steps to get down to the actual sampling within the PDF. We're not even at 5 here, but you'll notice that during this burn-in phase, we are always accepting a step downward in my value of x. It just, every time, steps right down. So it bounces down here for a little while. And then once you start to get into the core of the PDF, it becomes probable, if possible, I should say, to take a step back upward. And it starts bouncing around here. Of course, over time, this walker sort of goes down and really gets into the kind of core peak of the PDF. But this part here, as we're sort of trending towards the main core of the PDF, is called the burn-in phase, which is it's trying to find the peak of the PDF. And if you're doing that, you don't actually want to use those samples. If you go back to those first stages of the PDF, this is crap. We don't want any of this. In fact, you really need to wait till we're well past the sampling before it gets over here into steps of a few hundred before it's really bouncing around near the mode of the PDF. Okay. The other thing to note is that we aren't always taking a step. And so this chain has a lot of correlation structure. If you look at it, there's large sections of it here. This is 20 units wide. So it's sitting in one place for 3 or 4 steps. And that means if you're actually using a sampler and drawing these random deviates out of here, and you just pick a chunk of them, you could just end up with 7 samples that are all the same, all in a row. And that's not quite as random as we would like. We'd like there to be no correlations in our random variable. And what we'll do then is what we'll do is we're called thinning the chains here. And this process of thinning means just take every nth datum. Here I've sort of illustrated taking every 10th point. And the point you need to make is that, or the point when you're thinning is you need to be larger than the autocorrelation length of the sampler. And if you're larger than that, then the points will be relatively independent and you'll get real random draws from the PDF. So that's something that will help. That's intuition that will help us as we go to the future. Just as a point, since we're not even near the peak of the PDF, your burn-in phase in an ideal run would actually extend significantly longer than what I'm showing here. But this part is clearly a place where the chain is burning into the PDF. Okay. The final couple of thoughts here. Let's consider that acceptance fraction, the likelihood of taking a step. And you'll notice that that walker is kind of doing 2 things. First, it is finding the peak of the PDF, and then it's bouncing around inside that mode. The nature of this acceptance fraction is kind of different from an optimizer. In an optimizer, you're trying to find the local minimum or maximum of a function, and you only want to take good steps where you're walking uphill to the local maximum. So your numerical algorithm would never want to take a step backward and going downhill if you're trying to find a local max. But a sampler will sometimes accept bad steps walking downhill. So this happens, and that's what gives us the kind of genius here, is that if P of xi plus 1 over P of xi is less than 1, there's still a chance that even though that point is less likely, we're going to take a step to that point. And that's what makes this into a useful random sampler, is that it walks around and has a low likelihood of generating a low likelihood point. And that likelihood of generating a low likelihood point is exactly the likelihood from the PDF, given the way we have constructed this walker. Okay. Metropolis-Hastings is the simplest Markov chain Monte Carlo sampler, but it's quite graspable, and the intuition we get by looking at Metropolis-Hastings gives us a lot for higher dimensional spaces. The next step up in terms of sophistication is called the Gibbs sampler. It's a special case of Metropolis-Hastings that allows you to check one-dimensional steps, and this is very useful for working with a multivariate distribution. So you can sort of improve your compute efficiency, because you always want to be taking steps that you accept, even if they're going into a low probability space. Because a step where you're staying in one place, it's basically computationally inefficient. You always want to be stepping. You just want to make sure that you're only making that step proportional to a likelihood. So there's kind of a tension there. There's a lot more modern samplers. I think the most common ones these days are the no U-turn sampler and the Hamiltonian Monte Carlo samplers, both of which are kind of leveraging sort of functional optimization space ideas. And then there's this very popular package that is called MCEMCEE that uses what's called an affine invariant sampler, all of which have strengths and weaknesses that we'll start to get into next week as we talk about practically how do you use these more complicated Markov chain Monte Carlo systems. But for now, this should give you an introduction, and we can start to explore how an MCMC process works.